and we're going to go over it. So the first thing, we need a cover page. Okay, so the cover page, at least, we have a midterm assignment. We need your name and you need the title. So it's midterm assignment, ARCH360, something like that. Okay, so first, if I am a client and I receive a report from an architect or a construction company or whatever, it's not just a report. Report what? So I need the name of the client. I need so I need a title, and at least I need a responsible for who's responsible for the report. Then the second thing, it's a table of contents. Okay, so we have to add a table of contents. So table of contents, it's what the hell is this about? Yeah, so this is a report on energy efficiency of this building. The author, I am the author of this company or whatever. And now what am I analyzing? So I have to write first the table of contents. So the table of contents, it's a summary of everything that we have done and everything that our client is going to see on that report. So what is the first thing that we analyzed? This, okay? So what is this? Roof, walls, okay? So what is this? It's the analysis of details or details. We have walls, roof, and floor, okay? And this is the analysis of details. And what do we want to achieve with this? Compliance with the passive house standards. Compliance. What are the passive house standards in when it comes to walls, roofs, and floors? What do we have to comply with? We are doing this. So what? What do we have to look at? The R value, okay? So the R value, or if we have walls here, so the R value of this wall is 49. Is 49 good enough or no? It has to be 50. Well, this is 49.5. So it's so it has to be around 50. Yeah, the more the better. But well, it's around 50, it's good. Okay, so it can be 49, it can be 51, it can be 48. But if the wall is around 50, that's fine. If the roof has to be more than 50. In roof, we don't have the concept of the R value. In roof, we have in the roof we have the U average. Okay, because we have the R value of the roof rafter, we have the R value of the thermal insulation. And so this is 17, this is 55, and the U average is this value. Okay, so what would be the R value of the roof? Well, this is complicated because we can't calculate the U average. Well, we have to calculate the U value of each part of the roof because we have rafters and we have thermal insulation. And then with this one, we can calculate the U average. And if we want to calculate the R value average, that would be 1 divided by U average. Okay, so in this case, it would be 1 divided by 0.022. Okay, and that would be 1 divided by 0.022. It's 45. Again, can it be better? Yes. In roofs, it should be above 50. This is 45. It's not bad. We have this thermal insulation or the R value through the rafter. It's a little low, but this is good enough. Okay, so the average is 45. How can we fix this? Increasing the thermal insulation. So if we just go to the thermal insulating material. And we make it, here we have fiberglass. So if we, instead of 12 inches, we have more, we will increase this. Okay, so the more, the better. It's not mandatory, okay? So the passive house standards, the R value of the wall should be around 50. The R value of the roof should be around 60, and the R value of the floor should be around 30. Okay, so again, we are going beyond the passive house. Our goal is to design a zero energy building. If we meet these values, we will be close to the zero energy building. If we are far from, if the R value of the wall is 20 and the R value of the roof is 30, we will be far from the passive house standards. But it doesn't mean that if we meet these requirements, we will be designing a passive house buildings. There are more things that we have to check, but at least we need this. Okay, so if what's the conclusion of all these report? So at the end of this analysis, there should be a conclusion of our values. So in these conclusions, okay, so what's the R value of the wall? The R value of the wall is is 49.5. This is less than the benchmark, the R value of a passive house, that is 50. Okay, but the conclusion is it's close enough. The R value of the R value average of the roof, it was 45. 45 is less, it's less than 60, because this is the R value, the passive house prescription. Okay, so what shall we do? We should add more thermal insulation. Again, you can try to do this or to keep going with this R value 45. Maybe there are reasons that you can add more thermal insulation, because adding more thermal insulation means we have to make the element thicker and heavier. So probably there are structural reasons that we can add more weight to that roof. Okay, there might be reasons, but this is what you get. Okay, so you have an R value of 45. It's a little far from 60. And then finally, we have to do the same thing with the floor. Okay, so that would be the conclusion of our values. When we are doing this analysis, we are assessing something else, which is the condensation risk. Okay, when we are looking at these graphics, if there's an intersection between the temperature and the dew point temperature, that means that we don't have any condensation risks. If we look at the graphics, apparently there is no condensation risk in any of the details, so that's good. So that's another conclusions. No condensation risks. And why don't we have condensation risks? What did you do to prevent condensation? You don't remember? So the condensation risk is about the vapor resistivity of the layers that we have here. Okay, so let me open the Excel. One. That's the Excel file. So why don't we have a condensation risk, for example, here? Because the vapor resistivity of those materials, it's like this, okay? So we have this is the exterior. So let's look at the wall. So we have the gypsum board. This is the interior. The interior in the wall is at the top. We have the gypsum board. That's the interior finish. We have aluminum. Aluminum is the vapor retarder. Then we have fiberglass. Then we have air, the ventilated cavity, and then we have the wood. This is the siding. Okay. So the aluminum, we have something very thin. It's 1/10 of an inch. Okay, something very thin. If we type here 0, then the condensation happens. Okay, so if the condensation doesn't happen, it's because of the vapor retarder or the vapor barrier. Okay, so the vapor barrier is inside the thermal insulation. This is the most important thing that you have to remember. The vapor retarder has to be in the internal phase of the thermal insulation. If we don't have a vapor retarder, we have condensation risks. Okay, and it has to be something. The key point is this value, the vapor resistivity. Okay, so the vapor resistivity of this aluminum foil, it's 40,000. So that's the tape that they apply to the OSB board. So we saw that in Benson wood. It's just a film, it's a tape, so it doesn't have any thickness, but this blue or bluish or greenish layer that they stick to the OSB board, this is the vapor retarder. Okay, so it's something extremely thin, so we can type here 1/10 of an inch. Okay, so it's nothing, but that's the effect that it causes. And it has to be here because if I imagine that I don't have this here, okay, so that's 0, and I add another material. Oh, I don't have to, because I have the drop down list. Okay, so if I have here aluminum, and this is 1/10.1, what happens? That happens. Okay, so it's not a question, oh, I place the vapor retarder and it works. It works if it's placed in the right position, in the internal phase of the thermal insulation. If I apply the vapor retarder on the external phase of the thermal insulation, it will be a disaster. So be careful, because imagine that, that's why I asked Hans if they are responsible for, because they supply the material, but then it's the construction company, the one who places the wall. But what if you place it inside out? Who's assessing it? Okay, if you have the siding, okay, you have to be very dumb. If you have the exterior siding and the interior finish, you place it inside out. But what if you receive just the wall and then you apply the siding on site? It's very easy to, okay, so is it inside out or outside? I don't know. I place it the other way around and it will have this effect. Okay, so we have no condensation risk because we have placed the vapor retarder in the right position. If we don't have a vapor retarder, now it depends on the material. If we use fiberglass, most likely it's fiberglass or cellulose, most likely we will have condensations. If we apply here the polystyrene extruded, polystyrene is more reliable. it's a material that it's not affected by condensation. So with polystyrene, we don't have condensation issues. But polystyrene, it has the downside of the high carbon footprint. So that's why those guys are using the cellulose. If we use cellulose, fiberglass, we can have condensation issues. So we have to be very careful with that. Okay, so remember, here we don't have the aluminum. Okay, so I haven't applied the, if in addition, if I have this, I will even reduce the condensation risk. Okay, but even if I don't have the vapor retarder with extruded polystyrene, I reduce the condensation risk. So that's it. When we are working with the conclusions, why don't we have condensation risks? Because I have applied the vapor retarder in the internal phase of thermal insulation. Or you can say, I don't have condensation risks because I have used the extruded polystyrene. Okay, but these are the two things that we have to assess in this first point. We have to analyze the details. First, we have to meet these passive house standards, or at least we have to be close enough. If we are not, if we are below these values, okay, so I have to explain that I know that we are below these values, and there might be reasons because I have budget constraints or I have structural issues, whatever. But at least you need to know where you are. So if we are close to 50, close to 60, close to 30, that's fine. But if we are far from it, we have to. And then it's about the condensation risk. You have to avoid the condensation risk. So if you have this graphic, you can understand if you have them or not. If you have them, you have to solve it. So you have to apply this aluminum foil on the internal face of the thermal insulation, or you have to change the detail. You have to change the thermal insulating material. Okay, so those are the two things that we have to do. So that's the table of contents. First, analysis of details, and we have to comply with passive house standards, and we have to analyze the condensation risk. We are talking about condensation risk. It doesn't mean that if we have this, and in this graphic, we don't have intersection between the two lines, oh, that's fine. That depends on, because you see that when we have a board, we have a wall, the wall is not infinite. We have to put together two walls because they have constraints for transportation. So if they have to put together two pieces of wall, then they have to seal the joint between them. So if they don't seal this well, they can have condensation issues, even though they have used the vapor retarder in the right place. Okay. So at least with this detail, we don't have this condensation risk. But if the assembly of all the materials is not correct, no matter how good is your wall, you can end up having this kind of condensation there. Okay, so what's next? We analyze the thermal loads. So the second point of this table of contents, it's the thermal loads. And the thermal loads is the peak cooling and heating power. Okay, so this is what we have to analyze now. Thermal loads, peak cooling and heating power. And what software did we use to do that? It's Revit. Okay, so we analyze these peak thermal loads with Revit. So remember that we did this. Okay, and we analyzed two options. And what's the difference between the two options? The percentage or the glass percentage. Okay, so in the glass percentage, it's option 1. I don't know, the glass area was, I don't know, how many square feet? And option 2, the glass area, it was less. Okay, so you have to write it down. The glass area of option 1, glass area of option 2. And with this, what is the conclusions? Because after this, well, those are the conclusions. Okay, so it's the percentage of savings. With option 1, we have this cooling, we have this peak cooling, we have this peak heating in the lobby, in the rooms, in the total. And with the second option, and here we have, the only thing that is missing here is the glass area. So this glass area is add up all the window area, the same thing here. So if it's 50 square feet, and it's 20 square feet. Okay, so that's the only thing that it's missing here. But these are the conclusions of this second part of the assignment, is the percentage of savings. So that's it. This affects mostly cooling, as you can see. Okay, so we have percentage of savings. This is the total, the cooling and the heating. So we can save 23% of cooling, only 6% of heating. Okay, so reducing the glass affects cooling, not heating. So if I reduce the glass by half, I only reduce 6% of the heating peak load. So if I'm going to use the building mostly in winter, reducing the glass doesn't make sense. It makes sense because, well, in this building, we applied most of the glass on the south side. Okay, so if we had done this in the north, probably the heating would be much. Yeah, so the savings in heating would be significant. But if we place most of the glass on the south side, the heating savings, it's not significant because, so glass has less thermal insulation than the wall itself. But on the other hand, it can let a lot of solar radiation enter the building. So this is heat that we have for free. Okay, so okay. Think about it. It's counterintuitive. We tend to think that in this area of the world, heating is more important. So everything that I do, I have to do it to reduce the heating loads. Okay, reducing the glass affects mostly the cooling. What affects the heating? There are two things that affect the heating: the thermal insulation itself and the infiltration. We will talk about infiltration later. But well, as you can see, we have a percentage of savings, but the percentage of savings affects mostly the cooling. Okay. So we have thermal loads, peak cooling and heating power. What would be next? We have the thermal breach analysis. Okay. Smaller. So what's the thermal breach analysis? I use Therm. Okay, so that's the software that I used. And what are the conclusions of this analysis? So I have option 1 and option 2. So here I need more conclusions of this term analysis. And what are the conclusions? Well, first, what have I done? So here we have two options. The first option and option 2. So in option 1, what is the value that we are looking at? We are looking at this R value that comes from this table. Okay, so the R value of this floor to wall transition in this case is something between 6 and 7. R value between 6 and 7. It's very low, okay, because according to the passive house standards, we should have around 50 in the wall, around 30 in the floor. So in this detail, I have 6. It's quite bad. Okay, so we are far from having something. Okay, so with the second option, you added thermal insulation, and this value it's higher. So that value with the second option, the R value it's between 10 and 11. Okay, we are getting better, but we are far from the a good value that should be between 30 and 50. Okay, so again, can I make it better? Yes, you can add more thermal insulation. Now we can see where the heat is going from. So we have thermal insulation here, we have thermal insulation here, but the heat finds escape like that, okay? So I don't know, maybe I should have more thermal insulation there, or I should move this downwards. So there would be, or I can increase the thermal insulation. So there are things that I can do. It's getting better, but it's not quite good yet. Okay, so I think we should be adding more thermal insulation in this detail. So now we have to do the same with the roof, and that's what we're going to do today with therm. We're going to analyze this with the roof. So again, we will have to model a roof detail, a bad one, and then we will try to improve it and then we have to analyze. But this is important. If we don't have this table, I can't tell the improvement. Okay, so yeah, so this looks better than this one, but how much better? Is it worth it? Going from 7 to 10, it's not worth it, I tell you. So because doing this, it costs a lot of money. So look at that. We have a concrete slab here. So placing thermal insulation here means that we have to demolish the concrete slab and then place the thermal insulation and pour the concrete again. So that would be extremely expensive. For improving from 7 to 10, not worth it. Okay. So those are the options that our client is going to, it's not, add more thermal insulation. Yep. Is this enough? Nope. How much does it cost? A lot. Is it worth it? No. So those are the solution. It's not good. I wouldn't do it because it will cost a lot of money and the improvement is not significant. So those are the conclusions that we have to get here. What did we do first? This is the thermal breach analysis. And now we have the compliance with passive house. In terms of peak loads and annual energy consumption. Peak. Okay. And what did we use? What software did we use for this? Design Advisor. So with the design advisor, well, first, we need this information here. We need all this data of our building, the wall area, the roof area, the total envelope, the CFM, the ventilation rate, and this screenshot, it comes from this website. So here we have to make sure that we are in New Hampshire, Leland Hopkins. We have the envelope area, the floor area, occupancy. Why do we have 5 in average occupancy? We are dealing with the whole building here. Yeah, I told you that in this case, well, in a building like this one, in an educational building, the average occupancy makes sense because this classroom now has people that when this class finished, we don't have any. So what's the average? Throughout the morning, there are 15 people now and 0. So between 8 a.m. and 12 and noon, the average is 6 because we have either 50, 15 or 0. In an office building, if people are working 8 to 5, the average is the same as the maximum because everybody's working, and at 5 everybody leaves. Okay, so anyway, we can, but I think we did this with the average the same as the maximum occupancy. The maximum, it was around 20 because we had 4 people in the office, so that was 16, and 10 people in the lobby, 26. Okay, so it doesn't matter if it's 26 or 25. So the average, I don't know if this will affect that much. I don't know. Try, and if the values are the same, you can leave it this way. Okay, but I don't think it will affect that much. Anyway, we need these elements from the Passive House website, and we need to compare the annual heating demand, the annual cooling demand, the peak cooling, and the peak heating. Peak cooling and peak heating, we have taken this from the Revit analysis, so it should be these values. Okay, so yeah, you should use the whole building. I think you're using only the lobby or something like that. Okay, so you should use the whole building. So the peak cooling would be 78, the peak heating would be 44. And we have to use the second option. We know that the second option is better than the first, so we are doing this with the second option. So yeah, the peak heating, this value should be 44. And the peak cooling should be 78, okay? And now we have this analysis. This is kilowatt kBTUs per square feet. So the peak heating load, this value of 9.4 should be the peak heating. It's 44,000. Divided by the floor area, and the floor area is 1900. Okay, if I do this, it be 44,471 divided by 1923. Okay, so according to this is 23. It's not 9. Yeah, I think this is 29 is the okay. So 9.4 is the limit that we have here is 9.4. Okay, that's right. And you have the peak heating is 21. Okay, so 21, 23 doesn't matter. But yeah, I have to check that. Okay, so I have to check that you have done this correctly. So yeah, so we have this load. I don't know why you have 38 here and 44 there. Yeah, I think so. Anyway, with 44 instead of 21, it will be 23. Okay, but and this one it's 76. So 76, you have to use this 78, whatever. Okay, but I'm going to check those results. So if there's something that it's not consistent, I don't mind if it's 21 or 23. I don't mind because we are far from the limit that it's 9. But there should be some consistency between the numbers that you get in different parts of the assignment. Okay, so that will be the conclusion of all these. And then the annual bill, the annual energy consumption, it comes from this one. We have the annual heating, we have the annual cooling. This is 44, this is 33. Be careful because here we have kilowatt hours per square meter, and we have to turn this into yeah, let's do it because I want to see this number. We have the units. I know units are a pain in the neck, but we have to be careful because if we do this wrong, it doesn't matter. So what's the heating? The original units on the report is 44 units kilowatt hour per square meter. So that is, we need to a converter, kilowatt hour per square meter to a kBTU per square feet. And do we have this here? Yeah, so this is the kilowatt hour. It's 44. Calculate. So we have 138.8. Units kBTU per square feet. Let's double check. This is kBTU per square feet, and this is kilowatt hours per square meter. Okay, so if we look at this report, we have heating energy 44 kilowatt hour per square meter, and we have to do this in kBTU per square feet. So the annual cooling demand, it's not 14. Yeah. So if I'm not wrong, that is the okay. And in cooling, we will have 33, and we have to convert this into again kBTU per square feet. Yep, apparently that's the right way to do it. Forty-four kilowatt hours per meter equals kBTU square feet. Okay, so I want to see those numbers because I want to make sure that the conversion is correct. So we have to do this with heating, and we have to do the same thing with cooling. And then we have to compare this in kBTU per feet square yearly. Okay, so check the numbers again. And that's it. And finally, we have the compliance with the passive house standards. And now I have to do the I have to do the PV energy production. And what are we using? Revit. And with this one, we have option 1 and option 2. So what is the conclusion of this? Well, now we have the 22,000 kilowatt hour per year. And here we have 38,000 kilowatt hour per year. So what are the conclusions of this? So we have option 1, and option 1, here we have this value. We produce 22,900. So energy production, 22,900 kilowatt hours per year. Area of array is 99 square meters. Okay, so this is the area of the PV array. So we have 99 square meter. Option 2, the energy production according to this is 38,490. It's 38,490. The area of the PV array is 160. 173. Okay, so we have more production with the second option because the PV array it's larger. It makes sense. But now we have to offer our client 2 options because this is better in terms of energy production, but it's way more expensive because we have almost double the area that we have here. Okay, so this is, I don't know, it's not up to us make that important decision because it's about paying money upfront and then saving money in the long term. But that's the decision. What we can compare is that if we have here the total energy, so the total energy, we have 86 kilowatts hour per square meter. So we have the total energy consumption. Consumption is 86. We have to add up heating, cooling, and lighting. So it's 86 kilowatt hour per square meter. So this is 86 kilowatt hour per square meter. Okay. And how many square meters do we have? If we multiply this times the floor area, and what's the floor area? So here we have to be careful with the units because if everything is in international units, and when it comes to electricity, everything is international units because we don't have BTUs in electricity. So the floor area is 1,900 square feet. So we have to convert square feet to square meter. So we have 1,900. So this is 176 square meters. Here, so if we multiply this times 176 square meters, so the total production is 86 times 176. So this is 15,136. 15, 1, 3, 6 kilowatt hour per year. Okay, so with both options, we produce more energy than we consume. Okay, so with this option, we consume, if the consumption is 15,000, we produce 22,000. This option, it's even better, but now it's a question of, okay, so do we have a zero energy building? We do have a zero energy building with those numbers because we produce more energy than we consume. Good. It comes at a price. And what is the price? The energy, the PV array that we can even offer our client a different option. So what if I just produce exactly something very similar to the energy consumption, something around 15,000. So I have to reduce the PV array, so I can do that. So how much does it cost? A PV array that produces only 15,000 kilowatt hours per year. That would be probably the option that our client will be demanding. Okay, yes. So can you please give me an option because I want to have a zero energy building, but just a zero energy building because I have budget constraints. So can you please let me know the area or the number of panels that I need to meet that energy? So that would be a third option. Okay, so that will be the midterm. So basically, we have this table of contents. We have to analyze the details, condensation risks, then thermal loads in terms of peak cooling and heating power. Then I have to analyze the thermal bridge, and I have to solve those thermal bridges. I have to comply with the passive house. And then with this one, I can turn this into a zero energy building if I produce more energy than I consume. So by analyzing this, for example, if I can be happy, okay, I'm happy because I have designed a zero energy building. I have good details. I have, well, I don't need the passive house standards in terms of energy efficiency, but in terms of energy production, I do have a zero energy building. Okay, so it's not perfect because we don't meet passive house standards. And the worst thing here would be the thermal bridge, okay? So this solution to the thermal bridges, it's not the best. And probably we will end up having some condensation or some mold here in these details, even with the solution, because it's not good enough. Okay, so you're never happy with the result. So I'm here. Oh, I have a zero energy building. It's not enough because our client will have a zero energy building, but most likely in 5 years there will be mold in this part of the building because the thermal bridge is not quite there yet. So it's there, we don't have the solution to the thermal bridge, or we don't have a good solution to the thermal bridge.